starting on Wednesday and Friday, we're going to do the make a model thing like we did with regression. So we're going to do just a regression. So make sure you're here because to get full points, you actually need to be here. And then a couple things you guys learned is it may take a little bit of outside work, which is fine to do by delegation. It doesn't necessarily require like fully meeting as a group outside, but you may need to do a little bit in between classes. So just be aware of that. Keep in mind it'll be the same thing where I need a PowerPoint. Yeah, based on how things went last time, I probably need your PowerPoint half-passed, and then we'll start loading and presenting then. So it will stick with the same groups we had last time because you guys kind of have a routine. And I'll have a little bit of direction, but it'll be the same thing, 2 data sets where 2 groups get the same data set, that kind of deal. So, any questions on that? I really wish I was in this room. Okay. I have an idea.
With a fan?
There is a thermostat in here. I don't know if I can control it, but I'm going to try. There's a fan.
I need your face. There's like, we had that there.
Oh my gosh. No.
Let's get it. Wait, can we use the giant fan?
It might be kind of loud, but that's what you get.
It's probably going to be too loud.
But you're sitting in a chair.
Okay, there's a thermostat, but it's obviously not working.
We have a fan.
All the way. Maybe when we break out, we can turn the fan on. I'll get so distracted if we turn that fan on, I can guarantee it. Okay, so pull out your quizzes. All 3 questions. I looked at them all. That's good. That's really all we need to talk about. Okay, so the idea behind the Pearson residual is that, okay, I missed the light. There we go. That you subtract the number of observed successes minus the number of estimated successes and divide the difference by the estimated standard deviation. You don't really need to worry about understanding that too much. Then there's the Hosmer-Lemeshow goodness of fit test. The whole point of it is to determine if your model is fitting well. We're going to talk a little bit more about goodness of fit in the next unit. Most goodness of fit tests have their basis in the chi-square test somewhere. So we're going to talk about the basic chi-square nuts and bolts. But the Hosmer-Lemeshow has been specifically designed for logistic regression, and it works fairly well. It basically says my model is estimating what I want it to estimate in an acceptable manner. Okay, so the null and alternative hypotheses of the Hosmer-Lemeshow test. The null is that the model fits well. The alternative is that it doesn't fit well. So in this case, what do you think you want to do, reject or fail to reject?
You want to fail to reject.
Yeah, if you fail to reject, it means you have good fit. So that does not mean that everything is perfect. It's just another piece of the puzzle that's giving you positive reinforcement. But it's just one of many things we check. Okay, it's worth 6 points. Yes.
So we want a high p-value for this one.
Yes, the bigger the p-value, the better.
Why would they do
Yeah, that's what I was going to say.
So I didn't put that actual equation. I said what it was, and the difference, I didn't, kind of like I had my answer for number 2 is number 1, and number 2 I put the same thing, but using the predicted values. When you're
Oh, yeah, you can do that because there is the Pearson residual goodness of fit test. That's fine if you did that. Okay. Yes.
Okay, so if we have to have a high p-value, does that mean it has to be above like the 95 percentile in order for us?
No, it's just, you just don't want to reject. So you want a p-value above 5%.
So there's a very good chance of it fitting. Am I thinking about that wrong?
Well, it'll make more sense when we do do you remember the chi-square test statistic?
Remember? Yes. Able to use it right now? No.
I'll write it up this way, because this is what's the nuts and bolts of almost all of these tests, including the Hosmer-Lemeshow. So what you're doing is, remember that big test statistics have small p-values, right? Okay. So if we have a small test statistic, we tend to have a big p-value, meaning we fail to reject. So this, in a model, what would be an observed value?
What you actually collected,
That's what we actually observed, right? What's the expected value?
what you were kind of hoping for,
What
what was your thought?
Yeah, that's what the model
Theoretical.
predicts. So if you take your x and you plug it in, it's what it spits out as your pi hat, right?
Mhm.
Okay, so if your model is working well, how big do you expect this difference to be?
Very small.
Small, right. So in turn, what's that going to do to your overall chi-square?
Make it small.
It will make it small, which means what? Your p-value will be
Small.
big, right? So you can see that we want small test statistics. We want big p-values because that indicates that these two are close together, which is a good thing. It means that what we saw and what our model predicts, they're close. So goodness of fit is the one situation where one of the few situations where you really fail to reject. Does that make sense? Okay. And what basically what the Hosmer-Lemeshow test is doing is it's taking the basic of a chi-square and then it does some stuff to it. And we're not going to worry about exactly what it's doing to it. I'm just going to show you how to do the Hosmer-Lemeshow test. So, okay, so 6 points possible. Like I said, if you talk to that question about the Pearson residual is really vague. So if you write something about goodness of fit, that's great because there is a Pearson goodness of fit test that's mentioned in your book. So that's just so pass those forward.
So why do the air
And
conditioning?
today we're going to be using
It doesn't work.
the observed, not the observed, the obesity data in class again. So if you want to load it.
Obesity or the Donner Party, because they're opposite sides of the scale.
Donner parties for the in-class.
It is, and I never noticed that till you guys brought it up that I have Donner Party and obesity on the exact same assignments here. But yes, we're going to go obesity in class and Donner Party after we're done with this. Okay. So, all right. So the first thing we're going to talk about is what is goodness of fit. So there's a lot of ways to assess goodness of fit, but there's a class of hypothesis tests called goodness of fit hypothesis tests. And basically they tell you if doing the test is a good idea. And the idea behind it is to measure how close these are together. So the closer they are, the bigger the p-value, the better the fit. So the null is that the observed y's are equal to the estimated y's, meaning that what we get out is exactly what we observed. The alternative, so you've now seen it written two ways. It's two ways to really write the same thing, is that they're not equal or that they're different enough that it's a problem. So if you fail to reject, that implies you have a good fit. If you reject, it implies you have a bad fit. That said, the more data you have, the more likely you are to reject a test, right?
Mm-hmm.
You can actually reject when you have a good fit. So you have to be very careful dealing with goodness of fit tests because they are very sensitive to sample size. Make sense? Okay, so first of all, they don't work well unless you have a large data set, because if your data set is really small, you'll usually fail to reject, even if you have a poor fit, because you don't have enough data to find the poor fit. Does that make sense? Okay. If you have any outliers, they're almost guaranteed to make you, you can have 1 point that makes you fail the whole test. So you have to be careful with outliers. Also, like I said, you have to be a little careful because an extremely large data set, even if you're getting a pretty good fit, will often reject just because you have a large data set. So you have to be very careful about about goodness of fit tests. So remember, they're just another piece of that big puzzle that we have. They're not the end-all, beat-all into the answer. So they're just another piece we use to assess what's going on. So the 3 tests that are mentioned in your book is the Pearson chi-square goodness of test. This is used when your x variables are all categorical. So everything in your model is categorical. All your x's are categorical, your y is categorical, and then you divvy it up into the different categories. You have the deviance goodness of fit test, which works a little bit better than the Pearson goodness of fit test. But once again, it relies on categorical x's. So the reason why we're going to talk about the Hosmer-Lemeshow test is it can have categorical x's or quantitative x's. So if your x is something like weight or age or anything that's a quantitative variable, you really need to stick with the Hosmer-Lemischau test because those two just aren't even going to work. Does that make sense? So you'll notice this is the only one we're really going to cover. Okay, so there is no built-in function in R to do the Hosmer-Lemischau test. So when you get the slides, if you've not gotten them already, you're going to just copy this. Where'd it go? Oh, here it is. Okay. You just copy, and you're going to go into R Studio. I'm not sure it'll stay in there if you do it in R Commander. Just paste it, hit enter, and now it's in there. And as long as you save your workspace image when you exit R Studio, it will be there forever. So when you get in to do your homework, it'll still be there.
So you just put it in and hit enter.
Yeah.
Why do you do that in the studio?
Because I'm not positive it'll actually go into R if you do it from R Commander. It might, but I know for sure it will from R Studio. So,
Does your RMS have to be checked for this?
no. This is actually totally independent of the RMS package right now. For those of you who've done much with programming, you'll recognize the function, how to write a function. Okay. Okay, so this is just the instructions. So if you forget to save your workspace image or you want to try it again, or if later on you're doing something in R and there are a lot of these functions online that you can copy and paste and put into R. So not everybody goes to the bother of making a new package you can download and install into R. Sometimes you have to just go find a package and the function, copy and paste it in and save your workspace image. So this will give the instructions on how to do that. Okay, so we had a lot of trouble, with the Hosmer-Lemischau test the first semester, and then we found out what it was is the obese data set, and a lot of our data sets have missing values in them. And Hosmer-Lemischau totally goes to pieces if you have missing data, which should not be unfamiliar. We had that problem with residual charts and other things. So the first thing you want to do is take the missing data out. So I made a new data set called obese2. There are two ways you can do it. This is the actual code for it. So I'm going to go ahead and put this into our R Commander. And then,
So is this way better than just saying remove all?
I was going to say, or you can use the menus. Both work fine. So you can also go into data, active data set, remove cases with missing data. That will do the exact same thing. I think it uses a slightly different function, but the functions do the exact same thing.
Which include all variables.
Yeah.
You already have the check marked.
Did you keep it? Did you do it the other way? Just you'd have the old data set. Like, is that good to keep the old data set?
Yeah, I like to keep a record of the raw data in case I need it again. So that's why I always rename my data when I make changes. So you'll notice it uses NA omit, and then the other one says obese, complete cases obese. Those are two bits of code that actually accomplish the exact same thing. So either one of those will get you an obesity data set that has no missing values in it at all. Okay, then you're going to run the logistic regression model. Yeah, okay.
Is there a way to know that it worked by the first one?
You can just look at it and see if you find any NAs, but this is a huge data set, so it's going to be hard to look at it. Basically, if the Hosmer-Lemischau test works when you do it, it did it. If it didn't do it, that test will not work. Okay, so we're going to call this obese 3. If you remember, our Y is obese, and then the ones we found were significant. What do I want to keep? SCL. Okay. Because remember, we took everything else out last time. Now SCL was kind of borderline, so I decided to leave it in. It's gonna,
We don't have average GPA.
oh, you probably need to make it. Oh, remember how we did that last time? If you guys don't want to have to make it again, you can just save your workspace data, and then your data will be in there. Your workspace image, and then we'll hold your data in our commander. Okay. So I need the model first. And then the name of the function is Hosmer-Lem. By the way, these are two of the big guys in logistic regression right now. They just published a new book last semester. Then there's, so you notice this is the data set, and we picked the Y variable, the response variable, and then this one is the model with the fitted values. Does that make sense?
Yes.
I have a lot of confused looks there for a minute, so I'm like,
someone else answering.
Okay. So you put in Y and then Y hat.
We thought it was a rhetorical question.
Well, you look really confused, so, you know, I expect a certain amount of rhetorical, but there were a lot of confused looks. Okay. So basically, like I said, the Hosmer-Lem-Michel has its basis in the chi-square test. So this is the test statistic. Here's the degrees of freedom. And then the chi-square, we have a very small p-value. So what does that mean?
Reject.
So we're going to reject, and then what does that mean?
Means that it's not a good fit.
Yeah, we failed the goodness of fit test. There's something that indicates there's a poor fit. Now, before we found, these are the other things that help us assess some fit. So if you remember, we have the LRM. Our Summers D was 0.424, so it does better than flipping a coin 42% of the time. So it is helping us in that respect. What's the other thing we checked? We're going to look at something else in a minute. So we have that to help us out. We did the likelihood ratio test, and we now know everything is significant. But we have an issue with poor fit still.
This is Linda.
Yes?
What is the, I know it's the degrees of freedom is 8. Is there a general formula for degrees of freedom, or?
I'm trying to remember. I was thinking of that. Put that in there somewhere. I
Sorry,
think I
just
did.
shouldn't ask the question that I just.
No, that's a good question. I'll have to look into that. I always forget what it is. Because it doesn't make sense in the context of everything I think of with the degrees of freedom. So I'll look it up while you guys are working. Yes, ma'am.
Okay, so I said I couldn't find the function Hosmer-Lem. Does that mean I have to run that other thing you gave us first in order for this to work?
Yeah, did you copy and paste that function in there?
I put it in our studio.
Okay. Try putting it in our, sometimes you have to put it in our commander too. So put it in our commander, hit run on the whole thing, and it should work.
Oh, okay. Actually, I didn't highlight the whole thing in our studio and then hit enter. That was what it was.
Okay.
So I did that also.
Okay. So the next question is, why is this not a good fit? So things looked pretty good up until this point, but it could be that the selected groups weren't appropriate. Oh, I think that's what it is. It partitions the data somehow. Anyway, I'll look into it and I'll give you better information while I'm doing it. But it has to partition the data to a certain point, and it actually dumps it into categories in order to do this test. Maybe the number of categories it picked wasn't appropriate. So it could be the way the test was structured in the first place. It could be that we need more X's. That maybe our X's just they're not giving us enough information. It could also be that the logit model is not the correct model. With the logit model is the only model we're going to discuss in this class, but there are actually a lot of models that do this same thing. They get more and more complex. And remember we talked about the half-built subdivision?
Yeah.
It's even less built if you move on. So, anyway, but it could be that maybe logit just isn't the best model for you. You may have noticed there's another model in there called probit. And that has to do with the link function that's the normal cumulative probability function. Okay, that might be a better model. It may be that you need to transform one of your variables. It could also be that you have outliers. But the fact that we have a poor fit means it's worth investigating further. And this is something we're going to explore on Wednesday and Friday when you guys are working together a little more thoroughly. Okay, okay, so that's goodness to fit. Does that make sense? What's happening there? Yeah, everybody's like really red in this class. It's so funny.
So, quick question for the, when it says you might have outliers and stuff, for the last group project we did, we were able to look at charts and everything, or we're still going to be able to use the same charts, or just going to have to go to each individual variable and do like box plots for those?
You might be able to see them when you're looking for multicollinearity. I am going to show you something here in just a minute that may help you identify a few more.
Okay.
But it is more difficult to find outliers in logistic regression than it is in traditional regression.
Okay.
You notice it's just.
That's
you don't
kind of
have
what I
as
was
many
thinking. That's
people.
why when you said there may be outliers, I'm like, if you show us how?
Yeah, I'm going to show you.
Okay.
Another tool in a minute. Just one.
For our test, if it doesn't fit, are we gonna have to go through all these things and do it? So
I'm gonna in your homework. It's not so much. You're basically gonna say we had a good fit, we didn't have a good fit, and that's what we're doing on Wednesday and Friday. Is I'll have you address goodness and fit.
But on our
Start looking
test, do you
around.
think that we'll have to do that?
If you do, I'll give you some good guidance. But it'll probably be more like just tell me about it. That's a good question. It's a very valid question. Okay, so the next thing is there are residual plots that go with logistic regression. It took me about a week of phone calls and research to figure out what to do with these residual plots. You'll notice when you read your book, it'll be like, here are residuals, here are residual plots. End of story. And they don't tell you how to read them or what you're looking for. And so I finally got a little bit of guidance on how to do this. But there are two types of residuals. There's the Pearson residual, which we mentioned in the quiz. So, and then you have the deviance residual. And they both have their strong points and their weak points. You're not ever going to have to do these by hand. So I'm just going to kind of give you a little definition of what they are. And then we'll go ahead on how to compute them. So, let's see, we have our model that we've already run, and in order to get the residuals, you use this residual function. Oops. So you just do residuals. This actually works with multiple linear regression too, but you would use them to get different residuals. So you'll notice that we have the model name and then the type. So this will give us the Pearson residuals. And I get one residual per observation. I don't know if you ever noticed how big the obesity data set was, but we have 4,690 observations.
Are they saying that a lot of people are obese?
What was
Some
that?
of them-
We got a lot of samples.
A lot of obese people?
Yeah, apparently they've collected a lot of data on obese people. Well, and actually it's just people, as some of them are obese, some of them are not obese. So we're trying to predict if they're obese or not. And then if you want the deviance ones, you just change the type to deviance, click submit again, and you're going to get the deviance residuals.
So I'm a little bit confused at the difference between, why there's difference between the residuals for both tests.
They're just computed a little bit different way, and they give you a little bit different site. So, you know, in traditional regression, it's pretty straightforward what a residual is, what it means, and what the properties are supposed to be. Now that we're in logistic regression, as far as what a residual is, it's kind of hard to say because my y's are zeros and ones, but my predicted values are decimals. So they don't match up really well. Does that make sense? So like my predicted value, if I just take my predicted value minus my observed value, it doesn't make a lot of sense in logistic regression, whereas it made a lot of sense in multiple linear regression. And so they've had to come up with these different kinds of residuals to try to express that relationship a little bit better. But in doing so, we end up with different kinds of residuals, and it becomes difficult to know what we can do and what we can't do with those residuals. So you'll notice that I'll ask you to make residuals, and I'll ask you to do some plots, and you're just going to ask one question about the plots. And it's just kind of a yes or no question, but this is one place where you're going to look for outliers.
So, the deviance and the Hosmer-Lemon show were preferred over the Pearson for the model.
Yeah, but the
But is the residuals the same way? Like, do you prefer the other?
you know, as far as when I looked, it looked like everybody just did both. And nobody seemed to know which one performed better than the other. And I think part of it is because there isn't a lot of good information on how to appropriately use those residuals in the first place. But there is one rule of thumb I did finally find. So it's really funny, you'll notice in your book, they keep looking for normality. And so I said, well, do they have to be normal? Because do they look normal?
There's like a weird little normality clump over on the side.
Yeah, and so if you read the part in your book about residuals, is they'll be like, look, we looked at normality, they're not normal, but it never indicates that that's a problem, or that that was a base requirement for the test. And in all the reading I did, I actually found a similar thing, where, yes, they kept checking for normality, but it seemed like nobody cared. And I never did see a very good requirement that those residuals were supposed to be normally distributed. So honestly, I don't know why they keep checking for normality. But I put it up here so that we can talk about it when you wonder why you keep seeing it, because they're like, look, they're not normal, and then nobody cares. So, you know, whereas we really cared before, and now it's like, okay, I guess they're not normal, you know, let's move on. Okay, this is where you actually are going to do, this is where you do care. So your residuals will look like this. They have a really strange design. You have two lines of residuals. There's that whole cloud-shaped thing doesn't exist in this world anymore. You are going to get two weird curved lines. So the question you're going to ask yourself is, are they within the bounds of -2 and +2? If they go outside of those bounds, then you might have a problem. Once again, might have a problem. So this is an indication, this would be an indication of where the goodness of fit is going wrong. And so trying to pull everything together, I'm going to see what you guys come up with as far as where you might want to go next, except I'll take Steve's question. Yes?
Well, that's kind of going along with what you're saying. So basically, like looking for outliers and having other issues where you have issues of goodness fit, doing these really mean nothing except suggesting somewhere you might want to go look at your data to figure out what's going on with this group.
Right. This really is suggesting you need more work on your model.
Okay.
So if you guys, thinking of all the tools you have right now, so this is kind of a really stretching your brains right now, what are some things you think you could do to try to improve the situation? First of all, I'm going to ask you, does it look like you have a few outliers?
Yes.
Mm-hmm.
No.
I wouldn't say you have a few outliers, because you've got a lot of points. It seems like a continual trend. Miss Brianna?
I was going to say, could we try transformation?
This to me would scream, let's try a transformation.
I don't know if you tried this before and I missed it, but what makes these residuals look normal or not?
Well, just on the histograms.
Well then, what makes it look like they need to be fixed on the residuals?
Okay, so down here, what makes them look like something needs to be done is the fact that, see, this is at +2, the red line, and the other red line is at -2. When it goes outside of that
it's supposed to be in
range,
between.
yeah, if it's outside of that range, that indicates something is going on that shouldn't be going on. So yeah, exactly. This is when my first plan of attack would be, because remember, we already looked for multicollinearity, right? And we got rid of that. And what else did we do? We took out all the non-significant variables. Right now this says, hey, we probably need a transformation somewhere. So does that make sense? So that's kind of where we would go. And that's on Wednesday and Friday what we're going to have some practice doing. So I'm going to kind of leave this at that. Now, I need to show you how to make the plots. First of all, how would I make those histograms? You guys should be good at that. Just name those residuals, do the histogram, you're good. How about the bottom one?
Looks like fitted values against the residuals.
Yeah, so these are the fitted values. So this was OB.3 $fit against the two residuals. Where did the red lines come from? Actually, if you look at the bottom, I'm teaching you a new art trick today. So this lines function is a really nice function. There's also a point function that does something similar. So this is the basic code for the plot. So we had obs fit for x, obs res p, which is the residuals, for y. I put on a title, and then this lines function is saying put this line on the active graph. So what happened is I have to give it a couple of points. So I'm saying these are the x values, these are the y values. So this would put in the point 0.2 and 0.82 and draw a line between those two. Yes, Shane?
What was the top one giving you? Because I see you have the par and fro, you have the histograms, the bottom one are the QQ plots, or
Okay, oh,
plots.
I keep thinking I'm not in there. Okay, so this up here just gives me the residuals and names them.
Oh, okay.
So we'll start there. And I'm going to change, oops.
But they're not named when we do the residuals.
Right, so that just showed them to you, but I have not named them yet. So I'm going to name them first. So now they have names. And then I'm going to change, I was messing with my par before class, so.
So are those residuals from your original obesity data then, when it's not obese 2?
Yes, these are the ones I just showed you a little bit ago. I just named them now. But they're from the ones where we've taken the cases out. They're from obese 2. So, but and remember we had the model obese 3. Okay. So,
So that's your new name is obese done.
right. So this is the code to the histograms, and I'm not going to do that because you guys are good at this by now. You've done this 100 times. But then what I'm going to do is make a plot. So I'll show you what these pieces are doing. So here's, so this is a trick I'm going to teach you in R that's really nice. In R, you can build plots piece by piece. So every piece of the plot, you can like remove and add something on top of it. You can layer these plots on top of each other. So this is the basic plot. But for easy reference, I want to put those red lines so I can see exactly how -2 and +2 come into play.
So how did you pick those numbers?
Because that's just, that was the best guideline I could find anywhere, is that if you have residuals greater than 2 or less than -2, it indicates you have some trouble going on.
Okay, and the 0.8 is?
I did that because, that's a good question, but when I popped, okay, so I actually made the plot and then I looked at it and I could see that my x-axis went from 0 to 0.8. And so I wanted to start my line here and end it here.
So we should always just keep that 0.8.
Yeah, and I found with this, pretty much it's always goes to about 0.8 or 0.9 because remember your fitted values all have to be between 0 and 1. But usually when I use this function, because I've used lines a lot to add pieces to plots that need to be there, I just make the base plot, look at it, and then I can figure out where I need to put things. Okay, so see here's my plot right here. And when I run lines, it just adds a line to my plot. This is the same plot. And so the x is saying, put one, start here and at 0 and end at 0.8. And then the y values are 2 and 2. Does that make sense? And then to add the next line, I just do the same thing, but the only thing that changed is that now I go from -2 to 2 so that it's on it's down on -2. So now I can see that I have a problem a lot easier. So if you're making a plot for something, or you can actually just tack this onto your plot data, it just makes for a really easy reference. Did that make sense?
Yes.
Okay, I hope this isn't terribly done with me, but the 2 lines, these residuals have 2 black lines. Do all of these Pearson residuals have 2 lines?
Yeah, when you do your residuals, they'll pretty much always look like this. The question
Okay.
is, do they go outside of the bounds or do they stay inside
Right.
of the bounds? But yeah, they'll pretty much always look like that.
Is there a way to transfer one line and not the other?
To what?
No? I suppose there's no way to transfer one line, because the bottom line doesn't look that bad, it's barely going out of the lower bound.
It's, it's like with any model, if you've got a model in one place, you've just got a problem.
Yeah.
So, it basically, yeah, so.
So why are there 2 lines? I guess maybe I didn't pick up on that.
I'll be honest with you, I'm not entirely sure.
Okay.
Oh, okay. Oh, you're not
I
sure.
just know I always get too late. It's like
Oh,
I said,
okay.
I've had the hardest time getting good information on these residuals.
Wait, we're talking about the 2 red lines or the 2 black lines?
Black
The 2
lines.
black lines.
Oh, okay.
We put the red lines there.
That's true, we did, I know, I just did
Is there a pinkish line?
That is a projector.
Oh, yeah, that's just the projector.
Oh, it's just
in
the
this room.
projector.
Oh,
okay.
yeah.
It does that.
Actually, I have a guess as to why I have 2 lines. My guess is that one of these is successes and one of these is failures, would be my guess.
That makes
But I'm
sense.
guessing.
Yeah.
So,
You should write the book, and then you can clarify all this stuff
These-
Yeah,
that
there
people
you
don't
go.
get.
I wish. I don't know well enough.
But these categorical data sets we're using, like data survivor, data not survivor, that has 2 options, right? And it's categorical. But what if you had like a 3rd option? Like what if like there was like the solution was like a yes, no, or maybe? Would you then have 3?
I was actually wondering the same thing because when I used to do logistic regression, I did a lot of it back in grad school. I did a lot of my thesis and stuff, and I typically had 5 to 6 categories.
I thought the whole
It
process
doesn't
was
have to
like-
be 1 or 2. But I don't remember ever checking residual plots. So
Okay.
my guess is you would have multiple lines as you up the categories that
Sure.
you're up, but I'm not positive. So it would be interesting to see. Dichotomous. Dichotomous means 2.
Well, isn't that the whole point of logistic regression, is that the response variable is dichotomous?
It is used extensively when you have a dichotomous variable, but logistic regression is not that limited. It mostly means you have a categorical variable. But we're learning the dichotomous version of it.
Okay.
But yeah, you can use it for classification. Like if you have, so what did we use it on? We used it to select between 5 different models before, should it be model 1, model 2, model 3, model 4, model 5. And logistic regression is great for that. It just, basically if you were trying to figure out what category to put something in, logistic regression is a really good tool for that. So there are a lot of tools that'll do that, but logistic regression is kind of like your basic go-to. So, is this making sort of sense? Like, the main thing is you're going to have 2 weird lines. You want it to be between -2 and +2.
So technical.
And if it is, then that's good. If it's not, then if it's just a couple points, you might have outliers. If it's a lot of points, you might need a transformation. Does that help?
Yes.
Okay. Yeah, it's not like before where it's like, let's take a whole day about residuals. It's like, you've got 3 rules and you're good. So, and you just learn the lines function, which is really nice. Now, as I said before, there's another one that if you want to play around with it, called points, that will put extra points on your plot, if you want to point instead of a line. And you can layer these as much as you want. So for instance, if we were to do this for the and then, I should say for instance, after that wasn't applicable. But for the deviance residuals, we get this. But you can make your points go straight up and down. You can make them follow a curve. In fact, I'll probably post some stuff if you're interested. Do you remember that logistic curve, how I showed you the regression and then I put the logistic curve on it? I did that with the lines function, where I just added that on. So lines function is a really nice thing. And you can put a lot of points in there, so you can have big vectors for x and big vectors for y, and it'll just put the line in there. Okay, any questions? All right, so now you get to practice all of this with the Donner Party data. Oh, that's what's on our A classes. Yeah. Yeah.
Sounds like a wicked party.
So basically, you're going to check out the different residuals, and you're going to try Hosmer-Loesch, and then I'm going to let you try a transformation just for kicks. Not because it necessarily needs one, just to see.
So wait, so when we do the residuals, you just want us to talk about them and then just not do anything else with them?
Well, I want you to get them, plot them,
Yeah.
and then just say they're within the bounds or they're not within the bounds.
Okay.
Does that make sense?
Yeah.
I just did that.
But
So-
we aren't doing our transformation based off of the residual plots. We're just.
No. In fact, I'll give you a little teaser right here. Everything looks really nice on this, so you wouldn't come through and think, I need a transformation. So that's why 5 says, just try one.